Here as friends towards some aspects last topic in all solid state, that is electrical and magnetic properties. First we have to discuss electrical properties based on conductivity. It is based on the materials are classified based on conductivity. As conductivity is the term studied in electrochemistry, which is denoted by K, that is expressed in Siemens per meter. Okay, then as the magnitude of conductivity is magnitude of conductivity, how is it of the magnitude of conductivity, that is from 10 to the power minus 20 to 10 to the power 7, as the difference is 10 to the power 27 order. The difference is taken like that, and these are classified into three types majorly, that is some materials like silver, copper, iron, etc. they have conductivity K, that is of 10 to the power 4 to 10 to the power 7 Siemens per meter. Conductivity is exhibited by such materials which are known as conductors. Some materials show the very poor conductivity. Some materials show very poor conductivity, that is, observe here, the value is, as they are like wood, glass, these are materials exhibit a very low conductivity, that is 10 to the power minus 20 to 10 to the power minus 10 Siemens per meter, and these are classified as the second type known as insulators. And some materials are in between, their conductance is in between conductors and insulators, that is a third type, and they are like silicon, germanium, or such solids exhibit conductivity in between, that is 10 to the power minus 6 to 10 to the power 4 Siemens per meter conductivity. They are classified as semiconductors. So solids are classified into broadly three types based on conductivity, and the conductivity range or the magnitude is 10 to the power minus 20 to 10 to the power 7. It is 27 order, and they are classified into conductors, example silver, copper, etc. metals. Insulators are wood, glass, etc. And some are in between, they exhibit conductance. They are semiconductors, example silicon and germanium. Now one more concept will be taken to explain the electrical properties. Atomic orbitals of the metal combine to form molecular orbitals. Molecular orbitals are two types: low energy bonding orbitals, higher energy anti-bonding orbitals you studied. So some are filled orbitals, some are highly energy unoccupied orbitals. So therefore atomic orbitals modified, combined to give molecular orbitals. Molecular orbitals are two types: partially filled. This is a partially filled like this. This is a molecular orbital which is partially filled. Yes, which is overlapping with a filled band. Yes, form bands. These molecular orbitals form bands. This is partially filled band. This is a band filled, that is overlapping with a vacant orbital or highly energy unoccupied orbital. This is overlapping band. This is overlapping band. In these two cases, what happened? As the electron shift from this vacant position from this partial filled one to vacant positions. Here, filled band to unoccupied, overlapping, there is a shifting of electrons is possible. These two bands explaining conductance of electricity by solids, nothing but conductors. These two diagrams are related to conductors. But in case of semiconductors, what is observed? Yes, this filled band and this empty band, valence band. Energy gap is here very small. Energy gap is very small. Here energy gap is small. Energy gap is very small. Yes, not very small, I am sorry. Small. Here very small. Here small. And by heating or giving temperature, the filled band electron jumps from this orbital to highly energy unoccupied orbital. There is a shifting of electron is possible when temperature is supplied. So at higher temperature, semiconductors conduct more electricity. So their conductivity K increase with temperature. Why? Because the electrons jump from filled band to empty band. That is. In case of insulators, how is the energy gap? Energy gap between filled band and empty band. This is an empty band. This is a filled band. Empty band and filled band. How will be the energy gap? Energy gap is very more large energy gap. Large. Even though temperature is supplied, the electron is not shifted from filled band to empty band is not possible, and they are called insulators. This is band theory useful, and this is the classification of solids based on electrical properties by considering conductivity into three types. Conductivity values are given, that is answered, or band theory is taken, atomic orbitals converted to molecular orbitals. Molecular orbitals form bands, and some are partially filled band, that is the left hand side, some are overlapping bands, and there is filled band and empty band. Energy gap is less and energy gap is more. The energy gap is more means that is insulator. Energy gap is less, that is semiconductor. Energy gap is very less, that is energy gap between filled band and empty band is very less, that is called conductor. The conductivity of semiconductors like silicon and germanium, conductivity of silicon and germanium increase by increasing temperature and also by adding an impurity. Externally you are going to add a compound, that is called impurity, increased by addition of impurity. This process is called doping, and that is known as dopant. That impurity is known as dopant. For what purpose? To increase the electrical properties. Impurity is added. Impurity of two types. They are, yes, silicon, germanium. Yes, they are doped with trivalent impurity. Trivalent impurity or trivalent dopant. Pentavalent dopant. Pentavalent dopant. In these two cases, the process is known as doping, and there are trivalent impurities as well as pentavalent impurities. What will happen? Take normal silicon for our discussions. Normal silicon is bonded with another silicon. So each silicon is surrounded by 4 silicon atoms tetrahedrally in the solid material. Okay. Then this silicon, one of the silicon atoms replaced by trivalent impurity, that is also known as electron deficient impurity. Electron deficient impurity. Yes. What is a trivalent? It has 3 valence electrons. 3 valence electrons is observed in case of aluminium, gallium, indium. 13th group elements are examples to behave as electron deficient, as their outer shell has 3 electrons. So one aluminium is introduced in the place of silicon. So this silicon is replaced by aluminium. Aluminium is coming. Okay, here aluminium is coming with how many electrons? 1 electron, 2nd electron, 3rd electron. There is no electron. Okay, to share with silicon like previous one. So one silicon is replaced by aluminium, which is a trivalent impurity, and it has no sufficient number of electrons to make covalent bonds with the 4 silicon atoms. That's why in this place a hole is happened. As in order to satisfy this hole, an electron is jumped from neighboring one. Electron is here shifted, and at this place, by shifting of electron here positive charge, that is shifted, electron is given like that. So in the entire crystal, as electrons are moving in one direction and holes are moving in it, that hole with a dash charge. This hole is happening with positive charge, and it is a positive type semiconductor, p-type semiconductor. P-type semiconductor is resulted by doping of silicon or germanium with trivalent impurity or electron deficient impurity like aluminium, gallium, indium, which possesses 3 electrons in the valence shell. 4th electron is not there. That's why a hole is happened. That hole has positive charge. So positive charge holes are moving in one direction, electrons moving in another direction, and there is a chance of increasing conductivity is observed. And these type of semiconductors are known as intrinsic semiconductors. So p-type semiconductor is an example of intrinsic semiconductor. Now come to silicon with other silicon atoms tetrahedrally arranged. Okay, no problem. This is the crystalline structure of silicon, and that one of the silicon atoms removed by pentavalent impurity dopant. That is phosphorus, arsenic, antimony are the elements available. These are 15th group elements in the periodic table. Therefore, 5 electrons it is coming with the phosphorus 5 electron. First electron with this silicon, second electron with this silicon, third electron with this silicon, fourth electron with this silicon. One more electron is present. That electron on phosphorus atom start delocalizing and go through the entire solid material of silicon. Therefore, this is a mobile electron, delocalized electron. Delocalized electron, extra electron. Why? Because 4 valence electrons sufficient to bond with the 4 silicon atoms like previous silicon, and one more extra electron is present, that is pentavalent impurity. This electron is a delocalized electron. It stopped moving through the crystal and electrical properties increased. So this electron is a negative charge and it is known as N negative, N-type semiconductor. N-type semiconductor is the information. These are useful to prepare diodes. These are useful to prepare diodes. Yes, N-type and P-type semiconductors are useful to prepare diodes. And the diodes are prepared by constructing these diodes, these semiconductors. Suppose it is a N-type semiconductor, this is N-type semiconductor, these two are fixed with another one in the middle, sandwich. So here what is produced? So this is NPN diode. Means one semiconductor in the middle and other 2 semiconductors of second type. These are sandwiched and form a diode, NPN diode. Another one is positive diode, P-type semiconductor, P-type semiconductor. These two semiconductors are sandwiched with N-type. So this is a second type, and that is PNP type, PNP diodes. For what purpose these diodes? These diodes are used to. These diodes are used to. For what purpose? You remember? Used as rectifiers. Used as rectifiers. Next one is transistors. Transistors also prepared. How are transistors prepared? In this manner, by using diodes, and they are used to detect and amplify. Detect and amplify radio or audio signals. Amplify radio or audio signals. That's the main purpose. And photodiode is also there, that converts sunlight. Sunlight is converted to electrical energy by photodiodes. Oh, this is about applications of intrinsic semiconductors. They are N-type semiconductor and P-type semiconductor. They are sandwiched in this way. We will get diodes like NPN and PNP, and these are used as rectifiers. Therefore, transistors are used to detect and amplify radio signals and audio signals. Sunlight is converted to electrical energy by photovoltaic cells, that is photodiodes. Now today, large varieties of solid materials are prepared. Large varieties of solids are prepared. By which combination? Average 4 valence electrons like silicon and germanium. Like silicon and germanium, 4 valence electrons maintained by combination of two different, that is 13th group and 15th group combination. 3 electrons, 5 electrons, average 4 electrons. As that is copied from silicon germanium type semiconductors. 12th group and 16th group combination. What are those combinations? This is aluminium, gallium, indium. This is phosphorus, arsenic, antimony. And here 12th group is zinc, cadmium, mercury. This is sulfur, selenium, tellurium. As how do we take the combinations? As by the combination of these two, a solid material, ALP. By the combination of these two, gallium arsenide, by the combination of these two, indium stibnite are possible. Here, zinc sulfur combination gives zinc sulfide type material, zinc blende, and next one is cadmium sulfur, cadmium sulfide, cadmium selenide, mercuric telluride. These are the materials which are prepared to increase the electrical properties of the materials you are observing. And some other materials also prepared which are behave like metals, oxides of transition metal ions. As what you are taken, oxides of transition metal oxides possess electrical properties like metals, behave metallic properties. They are the combination you have to take titanium dioxide, chromium dioxide, and rhenium trioxide. This rhenium trioxide is behave like metal, like copper metal, and like in conductivity and color. Conductivity and color. Yes. And some other combinations is VO2, vanadium monoxide, vanadium dioxide, trioxide, titanium trioxide. Vanadium trioxide, titanium trioxide, as their properties depend on temperature. At low temperature insulators, at high temperature semiconductors, like that. These are the materials. These are temperature dependent conductors. Yes. Temperature dependent. Their conductance depend on temperature. This is about electrical properties. Now shall move to magnetic properties. Now look into magnetic properties. The magnetic properties are due to as electron. Electron behaves as tiny magnet. Why? Because electron is revolving from the nucleus and it is orbital moment, and electron around its own axis spinning clockwise and anti-clockwise. This is around axis. Around axis it is spinning. Due to these motions it has magnet. It behaves as tiny magnet, and magnetic properties are classified in this one. Some materials like Na plus, Ag plus, water, etc. are such materials are subjected to electromagnetic field. Electromagnetic field. The substance is weakly repelled by the electromagnetic field. What is the experimental observation? Weakly repelled. These are weakly repelled by external magnetic field. What is the meaning of, what is the result of this one? Yes, this results and it is described as diamagnetic material. Diamagnetism. Example, Na plus. What is the reason for diamagnetism? The reason here, in these materials, no unpaired electron. So that is due to absence of unpaired electron. Or other version is nothing but presence of paired electrons. One electron, the magnetic moment of one electron is cancelled by another electron. This magnetic moment is denoted by magnetic moment, spin-only magnetic moment. Spin-only magnetic moment mu B is equal to as 9.27 into 10 to the power minus 24 ampere per meter square. Any mistake are you observing? Yes. The mistake is related to units. It is not ampere per meter cube, it is ampere meter square. That is sufficient. Okay, this is useful information for both point of view. Okay, right, visible. Then come to second type of magnetic behavior you are watching. Some materials are repelling by, weakly repelled by extramagnetic field. They are called diamagnetic. As some materials like oxygen, copper 2+, etc. materials are kept in external magnetic field, they are attracted, weakly attracted by external magnetic field. What is observed? Weakly attracted by external magnetic field. As such materials are here observed and they are classified as paramagnetic materials. Paramagnetism. This paramagnetism is due to, here you studied in the first year, according to molecular orbital theory, as the magnetic behavior is explained by possessing two electrons, unpaired electrons in antibonding pi molecular orbitals. So oxygen is a paramagnetic material explained by molecular orbital theory, that is due to presence of, it is due to presence of unpaired electrons. Very, very important. Previous unpaired electrons are absent, diamagnetic. Here unpaired electrons are present, paramagnetic. As if you take iron, cobalt, nickel and chromium dioxide, these are materials. If you kept in front of the external magnetic field, strongly attracted. After removing electrical magnetic field, what happened? As they form, they are transferred into permanent magnets. Their magnetic behavior is not changed. Here, their magnetic behavior is changed in the absence of electric magnetic field, in the absence of by removing of magnetic field, external magnetic field, they behave as permanent magnets. This is known as ferromagnetic materials. Give an example to ferromagnetic material. This is third case. This is second case. First case is diamagnetic. As in addition to these three normal things, two other solids also observed, two other magnetic properties also observed that we will take very soon. Get ready. Yes, what is the reason for permanent magnetic behavior in the absence of, after removing of electric magnetic field? That here, what is observed? Metal ions of these materials form groups. Those groups are known as domains. Those domains are aligned in same direction in the presence of external magnetic field. That's why permanent magnetic behavior is resulted in this case. Domains. Now there are two other materials, even though they have unpaired electrons largely. Here also unpaired electrons present, and unpaired electrons domains are present. The domain like this. How do you define this one? The domains are arranged like this. The all domains are aligned in one direction. Right. Next one is some materials have domains some in number as. How are they in the direction? As this is upward, downward, 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 upward. This is the domain in one direction cancelled by this one, and this is cancelled by this one. Finally, domains are 5, but it exhibits less magnetic moment. Such materials are known as ferrimagnetic materials. Ferrimagnetism. How do you define? Unequal number of domains in opposite direction. That is the reason. Examples: ferrites. That is Mg, Fe2O4, Zn, Fe2O4, zinc oxide, iron oxide. Magnetite, Fe3O4 is another example magnetite. In other case, what is observed? As here 6 domains are present. They are arranged in opposite direction, but equal in number or unequal in number. 2 upward, 3 upward, and 3 downward. These are equal in number. So equal number of domains arranged in opposite direction. Net magnetic moment is 0. Here net magnetic moment not equal to 0. That is the difference. And this material is known as antiferromagnetic materials. Antiferromagnetic magnetism. How do you define? Equal number of domains run in parallel and anti-parallel. Therefore, cancel. Net dipole moment is 0. Example is MNO. This is the end of solid state with the electrical and magnetic properties. Have a nice interaction with you.